So as we consider a freezing pool or pond in the wintertime, it's kind of an interesting thing about water, and this is a really, really important thing about water, that it works this way, that we see this. And so when we look at, different substances, including water, we can look at the volume expansion. And water in particular is going to be really interesting. We'll look at that. This is how we calculate the volume expansion. Delta V equals beta times volume 0, the initial volume, times the change in temperature. And for solids, beta is about 3 times alpha. And so we're dealing with the three-dimensional expansion of, whatever substance that we have. And so again, we have our table of the different coefficients here. And, now we're going to be paying attention to volume expansion. And if you notice, right, for instance, with aluminum, 75 times 10 to the negative 6 versus, let's say, gasoline, right? Gasoline's going to expand, its volume much greater than, a little bit more, more than 11 or 12 times greater, right, than aluminum will. And, with the air, look at that, right? The air is really going to expand. And most other gases, expand quite rapidly with, temperature increase. So let's take a look at this situation with K4. How much will a window that has a length of 0.5 meters by 0.6 meters by 2 centimeters thickness expand in the difference temperature if in Florida it's 33 degrees Celsius per year, so all the way down to 0 degrees all the way up to 33. So go ahead and pause the clip and see what the volume change could be like, and then when you're ready to check, you can hit play to continue. Okay, so you definitely needed that. You need the glass, the expansion for glass. So why don't you go ahead and pause the clip now and give that a try. Okay, so the volume is 0.006 meters cubed, and so that's the original volume multiplied by beta there. So that's the expansion in meters cubed, what we look at there, and that's good. Okay, so now let's consider a pond in the wintertime. Let's say that, we've got a pond, and let's say, it's 9 degrees, and let's say that a cold front comes through. It's really nasty out. It's really cold out. Let's say it drops to like -7 degrees, really cold out. So this water is going to start to cool down. Now, what happens here is with water, it's very unique in terms of what happens, as you get colder temperatures. But that top layer, right, that top water, if it's exposed to -7, it's going to get colder. It'll go to 8 degrees, right? And so 8-degree water is more dense. 8-degree water will sink, right? And so eventually, the 9-degree water will come up, turn into 8. 9-degree water will come, turn into 8, and it's therefore the whole pond will then become 8 degrees, right? Once the whole thing is 8 degrees, if it's still cold outside, right, then that top layer will become 7 degrees, and then that 7-degree water will sink, and the 8-degree water will come up, or the 8-degree water will come up and turn into 7. So then the whole thing becomes 7. Then that 7-degree water will turn to 6 at the top. 6 will sink. Everything will become 6. Then everything will become 5. Then everything will become 4. And here is the key temperature here. Once the whole thing is 4 degrees, and let's take a look at that now. So let's say, now the whole thing is 4 degrees, right? It turns out that if it's still really cold out, let's say it's -7 degrees out still, this top layer up here will turn to 3 degrees, right? But it turns out 3-degree water is actually less dense than 4. So 3-degree water will float on top of 4-degree water. And it turns out 4-degree water is the most dense water can be. at any state. And that's very unique because you typically we're used to seeing as things get colder, they get denser, they get more compact. But 4-degree water is the most compact it can be. So that 3-degree water is going to float on top. And then it turns out 2-degree water is even less dense. So that 2-degree water, right, when this becomes 2 degrees, is going to float. And then 1-degree water will float. And then what's actually going to happen is it's going to freeze, and you're going to have a frozen layer on top. Now, as the layer is frozen on top, then you're going to have, this water below it that's maybe at 3 degrees, turn to 2, then 1, then freeze, then 2, then 1, then freeze. So it freezes from the top. And that's really, really important because, it would be terrible if this ice, let's say ice formed and that sunk to the bottom or something, or ice formed from the bottom. That would be real bad because if ice formed from the bottom, you got your fishes here, it's forming from the bottom, and these fish, right? These fish are going to run out of room, and then they're all going to die, right? They're dead. And so that's really important with water that it works that way, and it's a unique substance that way. The fundamental thing that we have with water, the fundamental molecule that's essential for life, works this way, and it's very important that it works this way. So here's a picture of the density. Well, this one is volume over temperature, and then this one's density over temperature. And so as you look here with this, and you have the squiggly line to represent, break in the graph, but as we get, 10 degrees, right? 10-degree water, the volume is still pretty big. But then as you get to, 9, 8, 7, 6, that same little section, same gram of water that we're dealing with gets smaller volume, smaller volume, smaller volume. But then if you look here at 4 degrees, right? At 4 degrees, it's the smallest volume you can have. And then once you get to, 3 degrees, 2 degrees, 1 degree, the volume starts to get bigger. And that's why, the density here, let's look at density. That's why the density is the most at 4 degrees. It's the most compact it can be. That 1 gram of water, is the most dense it can be. And so as you get to 3 degrees, 2 degrees, 1 degree, 0 degrees, here the density is less than it would be at a greater degree. So when we talk about force and area, this is going to be a really important thing that we talk about. Let's say that you had, a 5 kilogram mass, let's say. That's not very geometric, is it? All right, there we go, 5 kilogram mass. And, you're resting this on your hand, let's say. Okay. So you're holding this. And yeah, that's fine, right? Now, let's say you had a 5 kilogram mass that had a needle nose at the end, right? 5 kilograms. Now, this is 5 of those, 1 kilogram masses, right? So this is pretty huge. Would you want that right on top of your hand if this was like a needle nose, tip? Definitely not, right? Because this is going to hurt much more than this. This isn't going to hurt, right? You're just holding it. But this could maybe go through your skin, right? And so this has much more pressure. So pressure is force over an area. The smaller this area gets, the more the pressure is. So if we have the force of gravity with both of these, right? Same force of gravity, same force, but the area is much smaller here, and that's pressure. Pressure, the more force that you have, the higher pressure that you're going to get as well. And so when we consider pressure, we're looking at force in newtons, we're looking at area in meters squared, and then pressure in pascals. And so, we're looking at, a certain amount of pressure that we would feel. And then with a gas, right, the hotter the gas is, the more force on the walls there's going to be, and the more pressure there's going to be. And so if we consider, let's say that we have what's the pressure felt on a surface where there's a rectangular mass, 150 kilograms placed on it, and these are the dimensions. Let's find out when we have, let's compare the different pressures. And so if you want to pause the clip and determine, the different pressures for all the different, I guess there would be 3 different situations here, you can do that. And, the force of this is going to be the force of gravity, right? You have the 150 kilograms. So when you draw it out, you can draw it out 1.2 meters by 0.4 by 0.25. Go ahead and calculate what it would be like, standing up or on its side or whatever, the 3 different configurations, and we'll compare the different pressures. So go ahead and pause the clip and take a look at that. When you're ready to check, you can hit play to continue. All right, so we got the force of gravity, 1,470 newtons. And so the bottom area, if we had it laid flat like this, 1.2 meters by 0.4, that's the area. So the pressure of that would be 3,062.5. And we could compare that to, if we had it on its side of 0.4 by 0.25, right? The 0.24 by 0.25 side, this side right here. I'll shade it in here, this side, if it was resting on this side. Our pressure would be 14,700. And then if we had it on its side with 0.25 and 1.2, so if it was resting on this side, we would have a pressure of 4,900. So if we had it resting on this side, right, which is the smallest area, we would have the most pressure in pascals, PAs for pascals. Now, when we're talking about the gases, it's important to look at volume, pressure, and temperature. And so, we're looking at, the state of that system, and we're looking at, what's going on with that gas. And we're going to deal with gases that aren't too dense. And so we're dealing with ideal gases that are not too dense, and they obey the ideal gas law relationship that we're going to look at. So with this one here, K5A, let's say that we have an ideal gas, and let's take a look at the properties of this gas, with an ideal gas. So it cannot be liquefied or solidified, and so like real gases, and molecules obey the laws of mechanics, and so they obey Newton's laws. The molecules are point particles, and they each have negligible volume. And when they collide with the walls, the collisions are elastic. They're elastic collisions. The molecules have a range of speeds, and they move randomly as well. And so this is true. All these are true with ideal gases. And a real gas may be approximated by an ideal gas as long as the density is low. And so if you have too dense of a gas, it's not really going to obey what's going on with the ideal gas law here. Okay, so if you want to pull up the simulation, you can go to PhET and then go to gas properties. And then let's take a look at what would happen to pressure if volume is changed but the temperature remains the same. And so when you do that simulation and you try that, you can see what happens. And what you'll see is what happens in one of these properties that we're looking at, gas properties. And so go ahead and pause the clip, give that a try, and when you're ready to learn more about that, you can hit play, and then we'll take a look at it here. Okay, so with Boyle's law then, we're dealing with an inversely proportional relationship. The volume and the pressure, as long as temperature is constant, is inversely proportional. So in other words, as the volume gets bigger, right, as we get bigger in volume, pressure is going to drop. And as pressure drops, if we keep temperature the same, that's what will happen there, and that's Boyle's law. So volume is inversely proportional to pressure in Boyle's law. What we're going to be using for volume is meters cubed, and then pressure is going to be in newtons per meter squared. And then also pascals. That's what 1 Newton per meter squared is 1 Pascal.